Hello everyone, my name is Yehonatan Fridman and I'm a researcher at the IEEE and currently a master's student at the Ben-Gurion University. Today I will present you the work I've done with Matan Rusanovsky under the supervision of Dr. Gal Oren on ChangeChip, a system we developed for a reference-based unsupervised change detection for PCB defect detection. Now, think of a local factory which its manufacturing includes some electronic devices and PCBs. It probably does not have enough budget for expensive inspection devices like we know used in massive production companies. Zero-defect quality in electronic devices is very desirable to ensure high quality of products. So the factory seeks for a cheap, fast, and efficient solution to help the workers detect faults in PCBs production. By having a golden PCB for reference, defect detection can be achieved by visually comparing an image of the inspected PCB to the reference image. However, slight changes in imaging conditions can be challenging to a computer algorithm. For example, changes in background, positioning, and lighting. Therefore, a robust solution to imaging conditions is important in order to reduce false positives. If we take a look at some main ways of visual inspection of PCBs, we first note the manual visual inspection. Manual visual inspection by experts is the traditional way for inspection. As PCBs have evolved to become more complicated, multi-layered, and assembled with much tinier components, manual visual inspection has become very tiring, costly, and subjective task. Therefore, there was a growing need for automation in the PCB inspection field. Other computer algorithms and techniques were developed and applied along the years to support automatic visual inspection. Main techniques in computer vision are classic image processing, supervised learning, and unsupervised learning, but each has a unique disadvantage. Classic image processing involves analyzing and manipulating images, focusing on image characteristics like color histograms and edges. Seemingly, these methods are not satisfactory to produce a complete solution in complicated tasks in computer vision, since they cannot understand abstract features from the data. In supervised learning, however, labeled datasets are used to train algorithms to classify data or predict outcomes accurately. But PCB architectures change rapidly, and it is very hard to attain a proper and general enough dataset for supervised learning tasks. PCB assurance is currently a field with a large number of classes and relatively small amount of data per class. Another challenge for supervised learning is the variance problem. PCBs are comprised of several different types of components. There are examples of the same component type that appear different, and examples of different component type that appear similar. So it is very challenging to the task of classifying different component types. In unsupervised learning, on the other hand, patterns are identified in datasets containing data points that are neither classified nor labeled. Usually, unsupervised learning models are weaker than supervised ones since they lack the supervision of the field experts, and therefore, it is harder for them to be optimized against the knowledge of the experts on the training data. So the problem of defect detection is considered very challenging in computer vision, and more new algorithms and techniques appear in order to face these difficulties. In this work, we developed Chainchip. Chainchip is a system for unsupervised change detection in PCBs. It is based on the assumption that change detection between an inspected PCB and a golden PCB can reveal its defects and help an expert focus his inspection on these parts. Chainchip is robust to changes in imaging setting by trying to cancel false positive changes that are created by the imaging environment. Unlike many other works, as we see here in example, Chainchip does not aim to model or classify defect types, and also not to model what anomaly is. Summing up what Chainchip is, it is not dedicated to replace the field experts with anomaly modeling or classification, while it do provide unsupervised change detection with respect to a given golden and with robustness to visual imaging conditions. Now, let's see the workflow of Chainchip, the algorithmic stages applied from input to output. The first stage is the preprocessing stage, which applies image cropping, image registration, and histogram matching to eliminate the effect of background, positioning, and lighting. After this stage, the images should be more ready for comparison. Then the difference image is calculated, and image descriptors for all the pixels are processed by the PCA K-means algorithm, producing a clustering of the difference image into a certain number of meaningful classes of change. The next stage is the post-processing stage, which in this stage a heat map of the classes is created by giving each class a representative score according to an MSE heuristic. The classes then are clustered again into several clusters of significance, and the most meaningful clusters are reported as changes. Now let's dig into more details. In the pre-processing stage, the PCBs are first cropped. The objective of the cropping is to discard the background to eliminate its effect in case of any changes in background and focus the inspection on the relevant parts. Various of techniques for image cropping can be used here, but we choose to use deep extreme cut. For deep extreme cut, we need to provide only 4 extreme points on the margins of the object that we want to segment, in our case, the PCB. Deep extreme cut adds an extra channel to the image in the input of a convolutional neural network, which contains a Gaussian centered in each of the extreme points. The CNN learns to transform this information into a segmentation of an object that matches those extreme points. In general, there is a trade-off in segmentation tools between the effort required by the user and the quality of the segmentation. In order to get good segmentation of complicated objects, the user usually needs to provide more points or curves, for example, in standard graph cut algorithms. Because PCBs and electronic parts usually have relatively simple shapes, deep extreme cut fits this task perfectly, providing good segmentation results with minimal effort by the user. For the registration part, the SIFT feature descriptor is used. Features of interesting points are extracted by the SIFT algorithm and then are used to create matches between points in both images. It is worth to note that SIFT descriptors are invariant to uniform scaling, orientation, brightness changes, and partially invariant to affine distortion. The matches are then used as constraints to a perspective transformation matrix that is calculated by solving a linear equation. The transformation then is applied on one of the images to align both images together. On the top right image, you can see the matches found in our example. If you look closely, you can find some wrong matches, but as long as most of the matches correspond to the correct linear model, the algorithm can find it and discard the outliers. Histogram matching refers to a class of image transforms which aim to obtain a desired shape of histogram for a given image. This stage of the pre-processing is aimed to cancel lighting effects created by changes in lighting conditions. In this stage, we match both images' histograms. Just note that histogram matching is a global process, so it is of course not a complete solution when complicated and local shadows, for example, are involved. Various algorithms can be used for this part, but in our work, we choose to work with the exact histogram specification algorithm. Its approach is based on the definition of an ordering relation, which induced almost strict ordering on image pixels. You can see here an example of the algorithm for transforming an image histogram to a logarithmic histogram. The algorithm also works great with RGB images by transforming the images into the age's eye space, then matching histograms according to the eye component, and finally transforming back to the RGB space. This gives a good solution in both cases of optical and radiographic images. After pre-processing, we calculate the difference image. The more black the pixel is, the more difference it represents. As you can see, besides the true defects, some shadow and noise get relatively high intensity of difference. So now, at the art of the algorithm, we analyze the difference image to produce a clustering of the pixels into classes, hopefully separating the pixels according to their level of change they represent. In this part, we apply window-based analysis of the pixels, learning features and relations between each pixel and its surrounding. To do so, for each pixel in the difference image, we create a descriptor that is built from a window of its surrounding. We also concatenate the windows of the difference image in the 3 channels of RGB, since it may help learn more some relations in specific channels. Principal component analysis, PCA in short, is then applied on this set of descriptors to reduce its dimension by learning and keeping the most important directions of data. This process de facto eliminates the effect of noise and keeps the significant data for each pixel. Now, the K-means clustering algorithm is applied, providing us a clustering map of the pixels according to different levels of change. The K-means algorithm for clustering is considered efficient working on large datasets. Note that a disadvantage of K-means is that the number of clusters should be provided to the algorithm. In our example, we choose 16 clusters. This parameter can be tuned in a specific system to produce optimal results. This unsupervised change detection algorithm is a variation of a method applied in previous work for grayscale satellite images change detection. Now, how do we get meaningful results from this clustering image? For this post-processing stage, we use an MSE heuristic to assess the level of change for each class. For each class, we go over all its pixels and we sum the squared difference between the two images in all the three RGB channels. We then normalize the result to get a value between 0 to 1. The higher the MSE score is, the more significance of change the class represents. According to the MSE values, a heat map is created. We could have been satisfied with this heat map, but we also want to report as output only the most meaningful classes. Therefore, we need to find the threshold. Various techniques can be used here. We choose to cluster the classes according to their MSE values. We choose to use the db-scan clustering, which is a density-based clustering algorithm and does not need to be provided with the number of clusters. However, it do have a density parameter to tune. By doing so, we reduce the number of classes, in our example, 16 classes to 5. Now, we choose to discard the lowest cluster of classes. As you can see in the graph in red points, all these classes were gathered in the lowest cluster and are discarded. One can follow another policy, for example, discarding all the clusters except for the highest cluster of classes. This choice of policy can be tuned in a specific system for optimized results and exhibits a trade-off between the assurance level to the noise level of the results. Keeping the significant classes, we get a meaningful output with the meaningful changes between the PCBs. In order to evaluate Chainchip, we created a dataset, which we call CD-PCB, of 20 pairs of PCB images. Most are optical images, but some are radiographic. We synthesized some challenging defects and tagged them by the help of the field experts. Chainchip performed on CD-PCB with about 90% of success. For conclusion, Chainchip provides unsupervised change detection with robustness to imaging conditions. Talking about its limitations, as we said, visual changes are not necessarily meaningful. In other words, Chainchip does not provide anomaly detection. Also, Chainchip does not exploit learning techniques from previous data. Moreover, various of parameters are needed to be tuned in each system for optimized results. For future work, one can think of another way to choose descriptors for each pixel, to learn better the relevant features for a change. Also, other heuristics can be applied to grade the level of change for each class. In addition, involving learning from previous data can also leverage Chainchip performances. Thank you.